solo mandamos esto.
Ok, ahí ya
¿El
está.
archivo como tal o una liga de YouTube?
De que así lo pongo. Ahí ya está grabando.
Va todo hecho. Y en inglés.
Ah, ok. Sí, todo bien. Entonces,
Va.
nada más chico que se vea bien en la cámara. Mm, creo que así, ¿no? Todo bien. Ah, pero se tiene que ver en la grabación.
Se tiene que,
No, se ven ustedes.
Ah, ok, todo bien.
o sea, puedes compartir pantalla y no hay problema entonces.
Pero creo que así ya se ve bien, ¿no? Porque en la cámara se ve el PowerPoint. Va.
Ya.
Well, this is our MATLAB projected movement simulation. Our team is Alejandro Vázquez, Joaquín Vega, Mateo Zaragoza, and Cesar that is not here. But yes, he will arrive soon. Yes.
So, soon enough.
Well, these are the formulas we used using Euler's method. This is the drag force formula, which involves like velocity, error resistance, and a bunch of other characteristics of the error. And these are the position and velocity equations using Euler's method, which involves using the derivative of the original equation times the step size and the equation for the last step, like added, and that gives us the current value using the change of time.
Yeah, we use these four formulas just to update the position of the rock and in each four booklet loop, I'm sorry, that formulas go and go and go and are to update the movement in the position.
These are the values that we had like at the start. For the run, like we only used like 20 amount of rocks. This is the rock diameter, like the size, basically the rocks of the volcano eruption, the density of each one, and the drag coefficient and the air density that is used in the simulation.
Then we have the simulation limits. We just put the initial time that is 0 and the maximum time that is 200. And we put the number of steps in 200. Then the initial conditions. We create a variable of zero size n just to put the values in a matrix, and this will change later to make it easier to arrange clearing. This is just to make the procedure more easier. We do the same in Y, and then we put the initial position of the projectile, the rocks, that is 0, and the height the projectile is going to be launched to 1000. Then we have the initial projectile speed 201 and the angle 45.
That's basically like the simulation. First, equals the volume of the rock, the mass projectile, the traversal area of the projectile, like the area that is going to use in simulation, the time, just a minute, seconds. This is going to like calculate the whole time that's going to have the trajectory for the rock, the initial velocity in x and y, the gravity and drag force for the whole trajectory.
Yes, this is just we are in this part of the code. We are just like establishing the conditions, the variables to use it when we are going to
Plotting the graph.
Yes, this is just to put like gravity, and you're establishing the simple.
Yeah, the established values based on the initial condition.
Yes.
So in this, all this section is to plot the initial like volcano structure. This is not totally necessary for the plotting of the trajectories, but it is for like the visual of a volcano, right? So first we established 200 grid points, which will be the amount of points used to plot like the volcano surface. And then we use like a bunch of calculations to basically get the trajectories like that will establish the volcano's surface, right?
Like, yeah, drawing the actual.
Yeah,
volcano.
drawing the actual volcano, yes.
Which one is it?
Huh?
High exponent spread height radius in negative, that's a Gaussian form.
Yeah, that's a Gaussian form. We use it so that the
Revolution solid.
yeah, it's a revolution solid of like a single disk, and it uses like the distance from the center to like a radius distance to plot the volcano like the same. And we also use the height, no,
Concavity.
the concavity, yes.
What is
But
that?
there's
What is that concavity?
the concavity is like a difference between the height and a certain like concavity value that we establish here in the concavity percentage. And this helps us basically just create the concavity at the center and make it so that it looks,
Crater.
yeah, like a crater. And also here we do a limit multiplier. This is used so that because normally if you like change the height, because the surface of the volcano is a square, it would look like incredible, like really thin or really small. So like we use this value to make it so that the terrain around the volcano is always proportional to the height, so that it doesn't look weird with very high like heights or very low heights.
Yeah, you scale it to the size of your view.
Yes. And well, here we add like a texture based on this file name. And yeah, we set that texture, right? Yeah, here we put the labels of the plotting.
Yeah. This is just basically the part when we
Where we plot the volcano.
plot the volcano, to appear like to see like a volcano in the
Yeah, it
radius.
looks pretty much like the cool volcano.
Yeah.
And here, this is all the plotting of the trajectories in a 3D space, which it is a little bit hard to plot something 3D and 3D. Like you have to use the plot tree for the like the equation for plot tree. But basically, we do a 4 cycle of the amount of rocks there is, so it repeats for each rock. And here we use a rand so that for each rock it throws it in a different like
In a random direction.
around the volcano. And we actually apply that here, where we already have like the position formulas. We multiply the x position by the cosine of the radian of the radians, and the same but for sine in the y position, and that makes it so that it has the same magnitude but in a different direction. But here we have like all the formulas in Euler's form, like using so that it updates each cycle with the different drag, and the drag updates with the new velocity and such. Here's the formula for velocity that updates each cycle, the drag applying the previous velocity, and here like the acceleration, velocity, position, right?
Euler's method.
Yeah, with Euler's method. And here we use yp equals x, y, I, because previously we made a matrix of all x values, but equal to 0. So here we equal each of the I values to its current like x value. This is so that here, once we plot the new value, we can easily just say delete the value of x I minus 1, and that deletes the previous plotted value, right? And here it is so that when it reaches 0 or less, it stops because like it already reached the floor. And it also defines here, once the first projectile is over, the margins of the grid, yes. So it takes the maximum value of x and the maximum height value of all that projectile.
Maximum height.
Yeah, so and because the projectile isn't going to be ever like higher than that. It
So
just
will never be like, the camera will never be lower and the projectile will be like
uh-huh,
out of range.
it will just keep like
Track.
focused on all the projectiles.
Yeah, like you cannot have like a higher reach or a higher
Yeah.
height.
Than the
when you have
maximum in
range.
the first
Yeah.
one. Yes,
Oh.
yes. And
Oh, the first one, is it like stronger or faster? Or
no, it's the same. But we take, like in that case, when plotting the axis limits, we don't take the value of the projectile with the angle applied to it. We take the maximum value.
Okay.
So it will never get out of that range.
Okay.
And I think that's it. The only thing is this if that makes it so that if it's the first loop, it doesn't delete the previous projectile because it doesn't exist. And that's it for this part.
This is also the part when we, right here, to put the values in the titles.
Oh, yes.
And
Do they move?
The titles. Or what
Oh.
do you mean?
the values are updating like
Each loop.
Oh, yes.
Each-
yeah.
each row.
It refresh every time the values change. Yes.
Okay.
And then it draws like the sphere, and once it falls to y0, it just stays there, and the next projectile is drawn.
In a blue color.
Yeah, it changes color.
Nice.
This is where it's like in the air, and that's where it lands, and there are 20 projectiles.
Yeah, and the time, for example, does return to 0 every time like it throws a new rock. And here is the simulation once it's finished. I think this is with 10 projectiles. And it just looks like that.
You can also see from here like the maximum like height considered and like a really high value. So it will never be out of frame. And it will always be like keeping track of everything.
Yeah, it just takes like the maximum possible value. And I believe that's it, right?
Yes.
Okay, thank you very much. Let me give you some.
Do I stop the Zoom now?
No, keep recording.
Okay.
Cesar, would you write Euler's equation to solve for, well, given an initial velocity, initial acceleration, initial position, to calculate the next two steps, for example? Can you write can you upload the push of the screen, last from the second? Second from the last, yeah.
Yes.
Can you write the equation? I read it. Yeah, like, forget the first 2 points. You have one x0, b0, and a0.
Consider, I think, initial
X sub 0.
x sub 0. I don't remember the
No,
equation.
x0,
X0 being initial position.
okay?
X
Now,
stage.
you
I think
have the actual values,
the one from the
x0, v0, and a0. How do you get the next 3 x values? Can you write it down?
No, I don't think I can. I forgot the equation.
Okay, let's say the first one is x sub n plus 1. Can you write x sub n plus 1 sub n plus 1 equals xn plus dn times h.
And stands for sub-zero or initial velocity.
N, just n, times h. Yeah, that'll be like the first one to get the next point in x plus 1.
Okay.
What would you do next if you have an actual velocity and actual acceleration?
I think what the code actually does, well, in this case, it does for values, but it updates by subtracting for eliminating. But I think we can keep adding. See, it's also like the exponential formula, no, like for graphs. So like if you keep adding the values,
When you write
Absolutely.
the next position, like n plus 2. X n plus 2. How will you calculate that?
wouldn't be all times 2, no?
Which one?
Wouldn't be all times 2.
I don't know, it's my actual question. Like, how would you calculate the next point if I already gave you first one?
Mm, is it like something like this?
And like the velocity kept the same? Stayed the same, the velocity, or did it change from time to time?
No, like here's also changing from like the first value to second value.
I have a really hard time reading
Oh.
those. Here's plus Bn 3h.
No.
Plus 2h.
Times h.
Remember that you have an initial velocity and also an acceleration. Can you write like under the tenths word? Tenths? You put no up. Yeah. X0, V0, and A0. So you already calculated the next x position with the previous x and n values, x and v values. What is the next step before calculating the xn plus 2? You remember? Like the movement, like parabolic movement, is made of two differential equations, where the change of position with time is velocity, and the change in velocity with time is acceleration. You remember those?
No, I think so.
So, that is all four of these course. And the calculus part also. Yep.
I don't know.
Okay. Alejandro, can you explain to me why in the simulation you use a zeros vector instead of just calculating one and delete the previous one and delete the previous one? Like for example, in there, the first line, you are deleting the previous value of x.
In what line? This one.
No, those are like the initial values.
Should I return it to the code learning that we?
Le pongo el código.
Yeah, the one that is with the zero vectors. Yes, no, yeah.
Yes.
Why do you use like a whole vector of all the values? Where you just need to get the next value and forget everything else? What is the utility of that?
Because we put like this one in the base one and then update it with the loop in the like next in the code. Later in the code we use that to just like update it and change the value.
Well, if you're updating it, why do you need so many values? You just need one, the
Yeah,
one that you're plotting, right?
yes, but like I use this one to the base to create a variable with a value and then it changed what I don't understand because like
Yeah, for example, in the equation, the xn plus 1, that means you're calculating your next position with the values that you had before.
in which one?
The blue one, written by Cesar, the one in the middle, yeah. In here, I am saying that my next position is my current position plus a change in position. I have my current position now, and I don't have the previous one. But you decided to put a lot of zeros. Well, it's the same, but for velocity, that my Bn plus 1 is my previous Bn plus my change in velocity. In here, you just store every single value of velocities in x and y.
I think so because this formula that is used later, these like zeros, like also they don't influence in the in the formula, like they have a part, but it doesn't matter. Like
Yeah, it worked, but the sole purpose of using Euler method is not to do that,
oh,
isn't it? Like Euler methods is the fast way to calculate something with small enough precision for you to do it faster without using that much memory as to store all the values.
But wouldn't like storing pre-allocating values like zero also help with memory?
Yeah, but you still need a value for a zero, an actual bit for a zero.
Well, I don't really.
Like, would you do it differently then? Like instead of just using zeros?
Now with the information that you gave me, like, yes, but in this time we were like trying to update it like since we finished, like we do a draft and then we look like what we can improve and we don't improve that part.
Okay. Oh, thank you. Final 14. Can you go back to the friction expression? The very first one. Like before the code.
The formulas.
Yeah. For example, can you explain where are those letters? 1/2, what?
1/2 I mean, this one was the drag coefficient.
The C sub D is the drag coefficient.
This one,
Okay.
I think.
What is the P? What is the U? What is the A?
Oh, wait. I got confused. No, yes, this one is the drag coefficient, the force, the drag force. is
Yeah,
the-
in order
the
to
overall-
calculate the drag force of the friction force, you need that expression, but what is everything but the 1/2 and the drag coefficient?
Ah. I don't think the P. I don't think it's a position. I don't really remember like because I just like recognize it and I don't.
Well, can you tell me what is the values that drive the actual friction? Like the more you have, the more friction you have, or the less you have, the less friction
The
you
ones
have,
where
other than the drag coefficient, of course.
the density of the rock, I think so,
So if you had a lot of density, like a really heavy object, like a gold
Mhm.
ball,
That will
would
be,
that have higher or less friction than a copper one that weighs half of it?
it will have more friction, I think, like it's even
Which
greater.
number tells you that two spheres, one made of gold, 20 kilograms per liter, and made of copper, 9 kilograms per liter. Which one of those values will tell you that the gold sphere will have more friction than the copper sphere? That the heavier object has more friction than the lighter one.
Tengo la punta de la lengua. The friction coefficient,
The friction coefficient is the B or the C sub B. That's the drag coefficient.
This one is the drag coefficient,
Yes.
and this one is the friction, no. Yes, or no? I don't remember.
Come on, imagine it's not like a metallic spheres. Imagine two balloons. One filled with air, the other one filled with water. Okay? They're exactly the same material, exactly the same texture, exactly the same size. One weighs 1 kilogram, one weighs 2 grams.
Yeah.
Okay, so that's 500 times heavier than the first one. I let them drop down from the ledge 4 stories, and which one would have higher friction? The heavier one or the lighter one?
More friction.
Yes, the force of the friction.
The lighter, why was less heavier? Because it's like the bowling ball and the feather thing, I think so. Because I mean, taking the air resistance,
Yeah, the FD is different, but which value of all those tells you that a heavier one or a lighter one will have different friction?
the,
I just step outside and let them fall, 2 balloons, well, 2 grams and 1,000 grams. Which one will have more friction force?
the later, like the one
In how do you know in that equation?
is with the U.
Which you, what is that number?
The
The temperature, flavor,
It's-
color?
the atmosphere, no, I don't think.
En la parte del código está el positivo.
I don't remember the name.
Thank you. And last but not least, Mateo. Can you go to the actual Euler method in the code?
So this part,
Is that when you calculate the next X and next?
Yes.
Whatever. Okay, so when you have your initial X and V and A, what is the first value? Yeah, can you erase it? What is the first value that you calculate? The X, the V, or the A?
first the B.
First, the V.
First, okay, first we need the velocity, so that
Well, you already have velocity.
we already have an initial velocity, but for each step, we need to recalculate the velocity because it affects drag.
Yeah, but what is the assumption of the Euler method?
That the change of between one step and the next one is the previous step plus the derivative of the.
Wait, well, yeah, that's the way to calculate it, but the assumption is that you're going to maintain the same slope, the same derivative.
Yes, but
So if you're at 0,
Mhm.
you're going to maintain all the values of 0 until the next step.
Oh yeah, but in the next step it changes.
So,
So okay, when calculating the first step, we already have an initial velocity.
okay,
For all the next ones, we need to recalculate that velocity for then calculating the drag and then calculating the acceleration. First, we calculate the acceleration, but before that, we need to calculate the velocity for the drag.
so you
So-
start at time 0.
We start time
calculate
0. We calculate,
Position, next position,
no, first acceleration, then velocity,
then you.
then position.
Why the acceleration if you're assuming that your velocity is constant during the whole H time?
No. Oh, we need to calculate acceleration because the position equation depends on velocity. And velocity depends on acceleration.
Yes, but Euler's method tells you that you're going to calculate that next time,
No, yeah.
not this one.
Okay, so you're talking about the first step.
Like in X sub n plus 1, would you take Vn or Vn plus 1
No, we calculate Bn plus 1.
before calculating X plus 1? N plus 1?
No, we calculate Bn, and with that we calculate first Ax plus 1.
Okay.
And
So
then-
first you calculate the position,
Yes,
and then the velocity, and then then the acceleration, then the velocity. Okay.
yes.
Oh, yeah, that's what I expected to hear. And can you tell me, another one? How do you control the program for it to stop at Y0 instead of just going to negative numbers?
Okay, it's this part of the code.
Okay,
We basically take, it's this if. basically.
if I
If-
is less
Less than
zero,
0, we equal it to 0, and we plot that.
Oh.
Yeah, simple as that.
and, okay, I see a break function, like the simulation just stops.
It stops at 4 and it continues to the next one, the next row.
Okay, thank you very much. Okay, guys, thank you. You can stop the recording now.
Yeah.